Hello, hello, and welcome to this video. In this video, we will start the read through of documentation of Hashmap of Rush. Till now, we have covered vectors and linked list, and linked list facilitates stacking queues. So we have got Hashmap, and then we will cover hash set, and then we will move on to iterators. There are no algorithms for graphs. The reason is that graphs can be of different kind of nature, so the library does not provide a graph. So after hash map, we will move on to hash set. So we would have covered by then vectors, linked list, stack, queues, hash map, and hash set. So let's continue with this hash map. So as you can see, the constructor takes key and value with a random state. Random state we don't need to provide, and allocator also we don't need to provide, though we can. So the hash map implemented with quadratic probing and SIMD lookup. Now SIMD stands for single instruction multiple data. If you don't know what is SIMD, the simple thing you can think in terms of it that lookup is parallel in nature, or concurrent or parallel in nature, not concurrent, parallel in nature. By default, Hashmap uses a hashing algorithm selected to provide resistance against hash denial of service attacks. The algorithm is randomly seeded, and a reasonable best effort is made to generate the seed from a high quality, secure source of randomness provided by the host without blocking the program. Because of this, the randomness of the seed depends on the output quality of the system's random number generator when the seed is created. In particular, seeds generated when the system's entropy pool is abnormally low, such as during system boot, may be of low quality. Now, this on Linux is typically dev-u random. If I remember it, either dev random or dev random. I forgot the difference between the two. One is one comes from the actions of videos like keyboard input and mouse and various applications which you launch that creates the entropy pool. I believe that is dev-u random. So from there, it pulls the seed for the random number generator. The default hashing algorithm is currently zip-hash 1-3. So if you have watched my data structure videos, there was a video on a better hash map by Tidwall that implemented zip-hash. I do not remember exactly which variation, but zip-hash I have covered, though this is subject to change at any point in the future. While its performance is very competitive for medium-sized keys, other hashing algorithms will outperform it for small keys, such as integers, as well as large keys, such as long strings, though those algorithms will typically not protect against attacks such as hash denial of service. The hashing algorithm can be replaced on a per hash map basis using the default with hasher or with capacity and hash methods. There are many alternative hashing algorithms available on crates.io. It is required that the keys implement the EQ and hash traits, although this can be frequently be achieved by using hash-derived partial equality, EQ, and hash. If you implement these yourself, it is important that the following property holds. K1 is equal to K2 implies that hash of K1 is equal to hash of K2. In other words, if two keys are equal, their hashes must be equal. Violating this property is a logic error. It is also a logic error for a key to be modified in such a way that the key's hash, as determined by the hash trait, or its equality, as determined by the EQ trait, changes while it is in the map. This is normally only possible through cell, left cell, global state, IO, or unsafe code. The behavior resulting from either logic error is not specified, but will be encapsulated to the hash map that observed the logic error and not result in undefined behavior. This could include panics, incorrect results, aborts, memory leaks, and non-termination. The hash table implementation is a rough port of Google's fish table. The original C++ version of fish table can be found here. So if you're interested, you can go and look at the Swift table implementation. And this CPP on top gives an overview of how the algorithm works. So if you want, you can go and watch it on YouTube. Now, examples are we use the STD collection hash map. We create a new hash map of mutable type because obviously we want to insert data, book reviews. Then we insert adventures to Huckleberry Finn to string, my favorite book to string. Then we insert another element, Grimm's Fairy Tales, and value is masterpiece. Another key, Pride and Prejudice, and value is very enjoyable. Another key, The Adventures of Sherlock Holmes, and another value, I liked it a lot. So it should be I, not EYE. So we'll see the significance of this. Now we look for the key Les rebels, and we will see that since this key will not be found, we have got those many reviews, but less Les Miserables ain't one. Then we will see that the adventures of Sherlock Holmes has typo mistakes, so we remove it. Then we want to find Pride and Prejudice, Alice's Adventure in Wonderland. So we iterate on the to find array or vector. So we iterate on it, and on book reviews, we try to get the book. If we get some, we print the book name and the review. Otherwise, we print the book is unreviewed. Now, you remember that you take this by reference because strings can be quite large. So the get parameter will receive it by reference. Now we look for the keys, and it will panic if the key is not found. Pride and Prejudice, we want to try, and it is there, so it will be found. Now, if you iterate over everything, you can iterate like book, comma, review in book reviews. We print book and review. A hash map with a known list of items can be initialized from an array. So we have hash map, and we initialize from the array Mercury 0.4, Venus 0.7, Earth 1, and Mars. The values are solar distance, and the keys are the names of the planets. Then we have entry API. Hashmap implements an entry API which allows for complex methods of getting, setting, updating, and removing keys and their values. So we have a hashmap. Player starts of we create a hashmap new. Now here you see that type instance. Let's omit an explicit type signature, which would be hashmap str, u8 in this example. Now we have a function random start buff returns u8, and we just return a fixed value 42, can return random value. Now we have player stats dot entry health or insert 100. So insert a key only if it does not exist. Insert a key using a function that provides a new value only if it does not already exist. Player stats dot entry defines or insert with random start buff. Update a key guarding against the key possibly not being set. Let stat is equal to player stats dot entry attack or insert 100. We modify stat by random start buff. So it would be 142 because stat was not there. Then modify an entry before an insert with the in place mutation. Player stats dot entry mana and modify mana. We increase mana by 200 or insert 200. So if the mana entry is here, we modify mana to increase by 200, but it was not there, so we insert 100. Now users with custom key types, the easiest way to use hashmap with a custom key type is to derive EQ and hash. We must also derive partial EQ. So we have struct Viking, name and country as string. Now we implement Viking, we create a new function. We take two string slices, one for name, one for country, and we return a Viking. And we convert these slices to the strings. And that's how we initialize name and country. Now we want to create a hash map. Note that Viking derived hash EQ, partial EQ, and debug. Now we create hash map from writing objects with the values. Okay. So these are HP 25, 24, 12 as described here. So others are writing objects. Einar from Norway, Olaf from Denmark, Harald from Iceland. Now we use the derived implementation to print the status of the Viking. For Viking, health in Vikings, we print the Vikings HP. Now we look at uses in const and static. As explained above, Hashmap is randomly seeded. Each Hashmap instance uses a different seed, which means that Hashmap new normally cannot be used in a const or static initializer. However, if you need to use a Hashmap in a const or static initializer while retaining random seed generation, you can wrap the Hashmap in lazy lock. Alternatively, you can construct a hash map in a const or static initializer using a different hash that does not rely on a random seed. Be aware that a hash map created this way is not resistant to Hashdog's denial of service attacks. So we have hash map imported, and from hash we import build hasher default and default hasher. From std sync we import lazy lock and mutex. So we create non-random entry map, a hash map of string and vector of I32. We choose uh, build hasher default and default hasher. And then we create this hash map with hasher, build hasher default new. Then we have another static non-random map. We have a mutex, create a mutex variable with hash map, string and vector 32. And this time we create mutex new from hash map with hasher. Now, Hashmap's using lazy lock to retain random seeding. Random entry map, lazy lock, hashmap, string, comma, rect by 32, we create with the lazy lock, new hashmap. And the static random map, lazy lock, from mutex, we create this hashmap. So you should not worry about these advanced details unless you have progressed further in your study of hashmap. But it is still good to be aware of such things. Now we look at function new, which creates an empty hash map. We will go a bit and then we will stop. So we cover some important functions like creations and all, and then we will wrap this video. The hash map is initially created with a capacity of 0, so it will not allocate until it is first inserted into. So we create a hash map of str and 32 hash map new. Then we have with capacity, which will take a capacity argument, creates an empty hash map with at least the specified capacity. The hash map will be able to hold at least capacity elements without relocating. This method is allowed to allocate for more elements than capacity. If capacity is 0, the hash map will not allocate. So here with capacity, we pass 10 for 10 elements. So we do not care about nightly APIs. Then we have with hasher, where it will take a hash builder as an argument, creates an empty hash map which will use the given hash builder to hash keys. The created map has the default initial capacity. Warning: hash builder is normally randomly generated and is designed to allow hash maps to be resistant to attacks that cause many collisions and very poor performance. Setting it manually using this function can expose a DOS attack vector. The hash builder pass should implement the build hasher trait for the hash map to be useful. See its documentation for details. So we have hash map, we have a random state from hash. We create a new object of random state and we create hash map with hasher of random state. And then we can insert the values which we want. Then we have public function with capacity and hasher. So it will combine the two functionalities which we have just discussed. The documentation is same. And here you can pass the capacity and the state both. Then we have capacity, returns the number of elements the map can hold without relocating it. This number is a lower bound. The hash map k, v might be able to hold more, but is guaranteed to be able to hold at least this many. So if you look at map.capacity, it would be greater than equal to 100 if you initialize with capacity 100. Then we have keys, an iterator visiting all keys in arbitrary order. The iterator element type is ampersand single quote AK, that is, it has the lifetime A. So we create a hash map, and then we iterate over the keys, map.keys, and we copy the keys and collect into a vector. And then we sort the values, then it will become ABC. In the current implementation, iterating over key takes O capacity time instead of O len because it internally visits empty buckets too. Then we have function into keys. So it creates a consuming vector listing all keys in arbitrary order. The map cannot be used after calling this. The data element type is K. Now we have a hash map and we iterate on all keys and we collect it into a vector, which would be a vector of string slices. And then we do sort unstable, which gives us ABC. So you might remember sort unstable from our discussion, that sort unstable, for example, here we use sort. So sort maintains the order, but unstable sort doesn't maintain the original order. So it is unstable sorting, that is why it is named sort unstable. But its performance is slightly better than normal sort. Then we have values, an iterator visiting all values in arbitrary order. The iterator element type is V with the lifetime A. Now we create a hash map, similar hash map, and we call map.values dot copies copy dot collect, and we get values. We sort them. We get 1 to 3. On the current implementation, it is the same thing: capacity and length, complexity, and then we have values underscore mut. So it is an iterator visiting all values mutably in arbitrary order. The iterator element type is mutable V with the lifetime A. So we iterate over the values in mutable fashion and we increase the values by 10. Then ABC will become 11, 12, and 13 respectively. And the performance discussion is saying then we have N2 values, which will give us a consuming iterator. The map cannot be used after calling this, and the elements type is V. So like previous one, we collect map.into values. The analogous function was into keys. We collect them in a vector and we sort unstably. So we get 1, 2, 3. So in the current implementation, it's the same discussion. Then we have iter, which will give us an iterator visiting all key pairs in arbitrary order. The element type is K, comma V with same lifetime A. So we create a hash map. We have a count is equal to 0. We get an iterator and we increase count while visiting the value pairs, and eventually count will be 3. Then we have iterator mut. So it will give a mutable iterator and we can change the values. If you see this, the iterator elements type is value is mutable, but key is not. So you can only change values. We multiply it by 2, and then if you get the values, then there will be 2, 4, 6. And performance calculation is same. Then we look at len, returns the number of elements in the map. So if you invoke len, initially it would be 0. After inserting one element, the length will be 1. Then we have function isEmpty, which returns true if the map contains no elements. So here isEmpty would be true, here it is false. Now I think we can stop here. Let's see how much remains. There is quite a bit. So we'll finish rest of it in tomorrow's next video, which will come after 4 days. So we will start at where we left off. That is, we checked isEmpty, right? So we will start at train. So in the next video, we will finish this. We will start at train and we will stop here. So I hope that you have enjoyed this video and found something useful and you were able to learn something. So with this, I will take my leave and I will meet you again after 4 days with a new video on remaining functions of Hashmap. So thanks a lot for watching the video. Have a great day ahead and stay learning, stay curious, keep learning, and most importantly, enjoy.